Welcome to Lamar University in this year's JASON event, Oceans and Climates.
I'm Kelly McFarland from Orangefield Junior High and an Argo co-host.
I'm Moyling Tang from Brick City Middle School and your other co-host.
First, we'll go to Rollover Pass to find out what's in seawater.
Then we will find out why there are rivers in the sea.
Next, we'll see how weather can affect waterfowl.
Finally, we will see how rising sea level will change the Texas coastline.
So let's head to the coast.
Hello, I'm Terry Looney. Today we are here at Rollover Pass to look at the different water currents and to talk about some different types of water parameters. And so right now I can show you, this is Rollover Pass. This is the Gulf of Mexico, and up here we have Galveston Bay, East Bay, and Rollover Bay. Now, can someone tell me why this Rollover Pass is an important part of the ecosystem here? Yes, ma'am.
Because it's an estuary.
What is an estuary? Yes.
It's where the salt water meets the fresh water.
Excellent. Salt water meets the fresh water. And so we have fresh water coming down from Trinity River, and we have the salt water coming up from the Gulf of Mexico, and they are mixing in this area. Now that makes it a very special place where we have water of mixed salinity. And we're going to talk about salinity in a little bit. But the estuary itself, there's lots of grasses and shallow water places to hide, whereas if they were in the ocean, what kind of habitat might those ittle bitty babies have?
They have like predators and stuff.
Okay, so the estuary is a nursery. It provides shallow water, protection from predators, lots of nutrition, and that mitigating salinity that is good for babies to live in. Okay, now we're going to talk a little bit about some water quality parameters. The first thing we're going to measure is turbidity. Turbidity is the amount of suspended solids in the water. That's the stuff that makes the water cloudy. I don't want to use the term dirty, okay? But it is cloudy. So it's mud and organic material, could be fish larvae, all those little things in the water. And we use this instrument to measure that. Now, as you see, it's just a disc with black and white and a string. Now, when we look at our water and we know it's turbid, where does the turbidity come from? What might be suspended in the water that would make the water turbid? Algae and larvae, that's right. So when you see water that has a green color to it, the turbidity there is because of microscopic algae or other plankton. So all those factors go in. So when we look at water like a swimming pool, would there be much life in that water? No, we don't want there to be. But in this water, with lots of suspended particles, the fact that it's turbid tells us there's probably some zooplankton and algae. All right, now the way this works, we are going to lower it down into the water, and we're going to see when we can't tell the difference between black and white. So Mary's going to hold the string right here, and we're going to lower it till she can't tell the difference between black and white. You tell me when. All right, and then hold it right here. There we go. Hold that up and show them the Secchi depth. So this is our Secchi depth. It's only about 10 inches, not quite a foot. So we would call this water almost highly turbid. Now again, does that mean our water is dirty? No. We can't tell if there's any pollution here without doing lots more tests. But we can say the water has lots of suspended solids. What we're going to do now is we're going to look at salinity. And we generally measure salinity. We can measure it in parts per thousand, percent, or even conductivity, depending on what instrument we use. And so today we're going to measure the salinity of this water in different ways to see how it works out. Okay, so first thing we're going to use is a hydrometer. If you look, the hydrometer has a weight on the bottom, and it also has this little stem and we're going to see where it floats in the water. It also has a thermometer in here so we can measure temperature. So if you'll just set it down in there, go ahead and do both. And you'll notice when we do a test, we generally do it more than once. Sometimes there might be a flaw in one of our instruments. So here we go. Look at your hydrometer the best you can. Grab it right at the water line so your fingers mark where it is and pull it up. What is the number?
It's one below
1.02. And yours is 1.01. So they're very close. Okay, so record that on your data sheet. Next, we're going to read temperature, because temperature does affect the different measurements we get. Cold water, is the water going to be more or less dense? More dense. There we go. And warm water will then be less dense. And that's going to also affect how much oxygen it will hold. So tell us, what is the temperature? 78 Fahrenheit, 25 Celsius? Okay. Now, as you've had these out of the water and our wind is blowing, what might that do to your thermometer and your temperature?
It's gonna bring, the temperature's gonna drop now. There's not no water.
Probably, because it is pretty cold out here today. So that's why your reading would need to be taken pretty quickly and not just held out for too long. But the sun has been on there. Remember, we're just now getting the cooler temperatures. So the water has been absorbing heat all summer long, and it holds the temperature much longer than the air does. Look on your charts, and from your reading of your hydrometer, tell us what the salinity is. Here's our temperature. Find across the top the temperature. What was your temperature? So about 24. And then go down to find what was your hydrometer reading. We said 0.102. And we read across, so what's our salinity? 27.2. And it's parts per thousand. Okay, parts per thousand, ppts. There's 1 part for every 1,000 parts. Now let's convert that to units of measure. So 1 part per thousand is 1 gram of salt for 1 liter or 1,000 grams of water. Okay, now the next parameter we're going to test is pH. So it's going to measure acid or base from 0 to 14, 7 being neutral. Okay, so we're going to use pH strips. They have some indicator on them. You stick them down in the water for just a second, take them out, and then compare the color charts. And we actually have 2 different types, so let's do it. Go ahead. There you go. Go ahead. Usually seawater is slightly basic because it has calcium carbonate in it. And so calcium carbonate tends to allow for the buffering of pH. We do know that it can vary according to the amount of rainfall and whatever else is in the water. And with your wide range pH and your other one, we're seeing it's probably between 7 and 8. So that would be a normal measurement for seawater. And this is not full seawater, so we would expect it to be perhaps a little bit lower. Now, the next parameter we're going to look at is dissolved oxygen. Oxygen is part that allows all of the cellular respiration to go on, and the metabolism of all of your nutrients and everything to make your body grow depends on oxygen. But when we measure oxygen in water, we measure it in parts per million. When you go parts per million, fish want 4 to about 7 or 8 parts per million. You're breathing 21 parts per 100, and they breathe 7 parts per million, okay? Much different scale. You can't breathe underwater because you need a lot more oxygen. Fish get their oxygen from under the water. So what we know is if that oxygen level goes below about 4 parts per million, fish die. And you've all heard of fish die-offs in the summer. Sometimes there'll be millions of fish, and that's because the oxygen level got too low, probably because there were too many fish and the water was too warm, so it couldn't hold the amount of oxygen. And so it is very important to have the amount of oxygen in the water. Now I've got my oxygen meter, and it has a probe down in the water, and it's going to give us the temperature, and it also gives us the amount of oxygen in milligrams per liter, which is parts per million. There we go, 9.11, and we had 9.07. It's changing as the wind moves, as we shake, as I move the probe, as the wind picks up or the wind dies down, our oxygen levels are going to change. That's the good thing about having an electronic device, is we get real time. Now, this instrument is called a refractometer, and the way it works, it has a crystal here, and the light refracts or bends through that crystal. Now, if we put some salt water on here, and we'll close it, then this salt in there will make it refract or bend a little bit more. And we'll actually be able to look through the eyepiece and measure, read the salinity on here, okay? So, it's highly technical. Reach in there, David. Put some water on your finger and blop it on there. There you go. Come on. There. Okay. Make sure we don't have, see, there's no air bubbles. Then we're going to hold it up, and it's highly technical, okay? Where blue meets white, read the number on the right, okay? And tell me what, you take it, just hold it level. You see there's the big line with the 20, and then there's little bitty lines, and then there's another line kind of like on a ruler marking the half mark. That's 25. So see, it's just below the 25. Now, we measured salinity before with our other instruments, our hydrometer. What did you get on that?
27.
About 27. Okay, so we do have some variation with instrumentation, which does happen, which is why we use multiple instruments. All right, so we're going to go ahead and record our refractometer measurement as 24, what are units?
Parts per thousand.
Parts per thousand. Very good. All right, we have one more parameter. We're still measuring salinity, but we have another instrument. And this is a salinometer. It looks a lot like the oxygen meter that we did. Has electronic probe. So we're going to stick it down in the water and see what our numbers are. So here we go, down into our, as we see the magic numbers. Notice it's also measuring temperature, because we said temperature can affect the parameters. So we kind of let the numbers get stabilized. And this is measuring what temperature?
23.3 Celsius.
23 Celsius, and our salinity, it's showing 20.7 or 20.8. So this is showing a little bit lower salinity. Okay, so we've compared refractometer with 24, 25. We had our hydrometer, which was showing about 27, and here our salinometer is showing about 20. So we're going to go over, because these are things that change. Now here, hold that out there a little bit. Can you lower it down into the water? Just put it just a little bit deeper. All right, we're gonna watch, see what it says. And it's reading, oh, this is interesting. What number do you see now?
27.4.
27.4. That's interesting that it changed between there and there. Think about what's happening. We're reading it in the past. What's happening to our tide right now?
You're about to switch.
Yeah, but it was coming in. So,
Everybody go out.
right, and so the water was coming in. It's bringing saltier water from the Gulf in, and we actually collected the water in a bucket over that way a little bit, and it's been probably half an hour since we collected the bucket. So here we go again. The parameters of the water change all the time. That's an interesting thing to be able to see right here as we're doing our observations. And throw. Excellent. There we go. We have a cluster of ducks. Okay, we just got through putting our rubber duckies into the water, and what happened to them?
They followed the current.
Okay, but the wind is going this way, and which way did the ducks go?
The opposite.
That way. And you said it was because of the current. But look how hard the wind's going.
The wind went right over the current, over the ducks, and
Very good. So the wind went over, they were real small, and so the wind went over, but the force of the water was able to pull them. Now let's think back about our estuary situation. In a few hours, the tide is going to change, and what's going to happen to the water?
The baby ducklings are going to go the other way.
Okay, so our water direction is going to change, and so what's going to happen to the water from the bay?
It's going to go back and forth.
Going to go back and forth, exactly. And so we have a constant exchange of water, a change of nutrients, and so this makes the estuary a very rich area for the babies to grow.
The current isn't always the way that the wind blows.
My favorite experiment was about the dissolved oxygen that I learned that fish need and that it is very important to our environment.
My favorite experiment was probably testing the salinity in the water.
I learned about how different organisms in the ocean are affected by different parameters, such as salinity and turbidity.
I learned a lot about how the salt in the water affects how fish live.
Much of the mixing of fresh and salt water in estuaries is caused by A. Plankton, B. The fishes, or C. Tidal currents. The correct answer is C. Tidal currents.
All right, welcome. My name is Jonathan Brazil with the National Weather Service, and today we're going to be focusing on ocean currents and how it interacts with weather and climate. So what we're looking at here is a picture of the Earth, and on that we have a model of the ocean currents over the Atlantic Ocean. How we get these ocean currents to form is at the equator, there's heating due to the sun. And all the time at the poles is there's cooling. So there's an imbalance in the two. Weather and ocean currents are just ways of distributing that energy across the globe. And so you can see already we're starting to make the weather connection and the climate connection. Ocean currents, the surface currents, are primarily driven by the wind patterns across the globe. And along the equator there's always low pressure because it's very hot. Somewhere in the middle, in the subtropics, is a high pressure region, and then there's a low pressure region up here. Because there's a high pressure over here, the winds blow counterclockwise around it. So you have easterly winds here, and then they turn and go from, out of the southeast, then eventually north, and then back toward the northeast. So what is that doing? That's carrying warm water from the equator poleward. So it's taking the heat and bringing it poleward, so where it's not as warm, but in the end, after you distribute this heat, well, what do you think's happening up here? It's a lot warmer up here than it normally would be, given all things being equal. Like over here, for instance, in Maine, it's very cool in the winter compared to what it is over here in England, and that is due to this current, which is what we call the Gulf Stream. So you can see it starts here, goes through the Gulf, and then carries all the way up in the North Atlantic toward England. Here we have a cold current that is coming south. This is very cold water, and it's the Labrador current, and it gets caught up into the Gulf Stream as well. And they end up mixing, so the cold water goes underneath the Gulf Stream because warm water sits on top. It's like we're watching a river moving through a big ocean, is really what it is. These little circles, these are eddies within the current. And these eddies are almost like weather systems that we feel every day. This particular one is the one we call the loop current in the Gulf of Mexico. And it's important for weather forecasting, and if there's a hurricane that goes over it, it has a lot higher heat content in the water there. So if a hurricane goes over it, it's able to get more energy, and it's going to be stronger. This happened with Rita in 2005.
Why is the Gulf Stream warmer than the outside water?
Okay, the Gulf Stream is coming from this warm water here in the tropical Atlantic, Caribbean, and the Gulf of Mexico. The water here is very warm. There's this narrow ribbon of warmer water that gets carried along with the current. And again, the current is nothing more than just the wind pattern on the globe here. Okay, here we've moved over into the Pacific Ocean, and the winds are not disturbed by land masses as much as they are in the Atlantic. This plays a very important role in not only in our local weather patterns, but over the entire globe. And we've known this for quite some time, that, you know, watching what the ocean currents do out here affects the weather on a global scale. Some years, for whatever reason, we really don't know why this occurs, but the winds here will get light over in this part of the Atlantic. And so this water stops moving toward the east as fast. So what's going to happen over here is the water is going to get warmer than it would normally. And that affects the whole global circulation pattern as far as how the winds flow across the globe. And that is called an El Nino. For us, El Ninos usually bring cool and wet winters. And so, you know, if we can forecast what's going to happen out here, you know, say several months in advance, we can say that the winter is going to be cool and wet or warm and dry. The opposite of that is a La Nina, and that's when the winds increase in speed and they carry more water off to the west than normally would happen. So that warm water here is taken over to this side of the globe. And so the water here, once it's carried away, this water's got to be replaced. And that water comes from underneath. And so that water is cool. During a La Nina, it becomes cooler than normal. And so again, that affects the jet stream again. That means that our winters will be warm and dry, typically. That also means that we usually see less hurricanes in the summer as well. That's why we watch this quite often before making a long-range forecast. It doesn't always work out that way because you can see there's a lot of randomness to this. So everything doesn't work out perfectly, but we can say with some degree of certainty what's going to happen by looking at what's occurring out here in the Pacific.
After Jonathan Brazel's briefing on sea surface currents, the Argos got to Skype with Dr. Diane Stanitsky, one of this year's JASON host researchers and director of NOAA's Adopt a Drifter buoy program.
Hi, my name is Diane Stanitsky, and I'm a program manager in NOAA's Climate Observation Division, and that's part of the Climate Program Office. We talk about ocean climate primarily, so today I want to talk with you about NOAA's Adopt a Drifter program. I'm the coordinator of that program, and I'm very excited that you're all going to get involved by adopting a drifting buoy. What is a drifting buoy, you might ask? It's an instrument that helps us monitor sea surface temperatures across our oceans.
How many buoys does NOAA track?
Right now, we have over 400 of them out across our oceans monitoring ocean climate.
How do we track the buoy?
The buoy transmits data directly from a transmitter on the top of the drifter, and it sends the data up to a satellite. And from there, data are sent to the NOAA Atlantic Oceanographic and Meteorological Laboratory, and that's in Miami, Florida.
Where would our buoy be released?
It depends on the exact timing and ships that are out across the ocean. It can be released in any of our oceans, and the likelihood is that it will be released in the Atlantic or the Pacific Ocean. It's unknown to date, but I'll let you know as soon as we identify a ship that's ready to deploy your drifter.
Where do you think it would go?
Depending on where it's deployed, it will move in the ocean currents, and your job is to find out where it goes by monitoring the drifter at the Adopt a Drifter program website. There's a website that you can go to see your specific drifter amidst all the other drifters, and that website enables you to track it as it moves in the ocean currents, through the warm ocean, through the colder ocean currents, and it's pretty exciting to see where they go. Sometimes drifters move in very interesting directions that are very unanticipated. So that's our job together, is to forecast the movement of your drifting buoy.
Why is knowing the sea surface temperature important?
Sea surface temperature is one of the most important variables across the ocean that we can monitor. Scientists are very interested in it for a couple of reasons. The first one is that it tells us about the heat that's within the ocean. The sea surface temperature is just the temperature at the very surface, but below that, we've got a huge body of water that often builds heat content. And through that, we can understand how much energy might be available for hurricane potential and also just for storm formation and how a storm might form over the water. It's usually dependent on the energy available in the ocean below it. And also, it helps the oceans flow. Where you have colder water and warmer water, the oceans flow in different directions. And that transfers things like marine animals. It can transfer marine species, help them in their migration paths. So there are many key reasons.
So yeah, they released the buoy here. So it's going to follow the Gulf Stream. It could stay inside the Gulf Stream or get caught in one of these eddies, and then it would take a while for it to get back into the Gulf Stream and then back up head up toward Europe. So it'll be neat to watch, to see actually what happens. Yeah, it's really hard to say. Again, it's like predicting the weather. You know, if it's inside this main stream, it'll be pretty easy. If it gets caught in one of these eddies, yeah, all bets are off.
Ocean surface currents get their energy from A, the sun, B, the wind, or C, the moon. The correct answer is B, the wind.
My name's Marty Briggs. I work for Huntsman Corporation, and I want to tell you a little bit about our wildlife project, mainly targeting the mottle duck. I'm going to show you all what a mottle duck looks like and tell you a little bit about its life, its history, and its ecology. This is a mottle duck right here. They look a lot like a northern mallard. The male and the female look almost exactly alike. The only way you can tell them apart is by the coloration in their bill. You don't find them anywhere else except right here along the Gulf Coast. You find them in Texas and southwest Louisiana. Back in the 80s, we had probably 60,000 birds. Now we're down to about under 30,000. So they have become a bird of concern, and the Fish and Wildlife Service and the Texas Parks and Wildlife have been watching their numbers. So we had a few of them out here at the plant, and what we wanted to do is we wanted to provide them with quality habitat to keep them in the area. When we started doing this, their numbers really started to expand. So we started doing a lot of management work, like trapping our predators and creating moist soil units, that's when you take your land and you keep your water at just at a certain depth where it's just moist, it's not too deep for other predators. And what we want to do is we want to create a balance. You don't want to trap them all out, but you want to get it to where they're not making that mottle duck number decline. Then we found out that there were a lot of people in our area that didn't know about a mottle duck, didn't know what a mottle duck was, and didn't know that they lived just here. We started getting with the local schools, and they started getting interested in it, so we tried to involve them. So now we have biology classes, environmental science classes, even our wood shops, our welding shops. This right here is a wood duck box, and the wood shop classes have started making us several nesting boxes. This one here has a smaller hole for a wood duck, and they make some larger ones that have a bigger hole for a black-bellied whistling tree duck. Now, since our wildlife project has started to expand, we're starting to bring a lot of other wildlife into the plant. These black-bellied whistling tree ducks, we've only had them now for just a few years. They're from Mexico and Latin America, and they've started to migrate up to North America to nest. And we're going to start providing them with even more nesting boxes. The school district has provided us with a lot of them, and we're going to try to get with some scout troops and stuff like that to put them up in some of our areas. Do any of y'all have any questions about our mottle ducks or anything?
Why do the tree ducks migrate over here?
Our black-bellied whistling tree ducks, just like I say, just started migrating a little bit further north a few years ago. And just about all your wildlife changes is man-induced. We have different land uses now. We used not to have near as many trees down in this part of the country. This was coastal savanna. It was more marshland. Over the years, it's been drained for development, subdivisions, and that kind of thing. And as people come in and build houses, they plant trees. That kind of habitat is a lot more enticing for these black-bellied whistling tree ducks. We actually have a lot of species that have started to migrate northern. The Mexican national bird, the caracara, is starting to make its way into North America. I've seen a lot of changes in my life, you know, as far as wildlife goes, and y'all are probably going to see some of y'all's too. A lot of it's weather pattern. Most of it is man-made conditions, just land use. The changes in land use has so much to do with wildlife. Yes, ma'am.
What type of predators do y'all trap?
Possums and raccoons and alligators, and actually the feral hogs, they're also a predator. We live trap them and we relocate them. Anybody else have any questions? Yes, ma'am.
What do mottle ducks eat?
Mottle ducks start off for their first 3 weeks of age, whenever they're just hatched. They'll start out on invertebrates, and mainly midge larvae and water scuds. It's soft invertebrates that they find in the water. And then after 3 weeks, they start to eat seeds a little bit, smaller seeds. And then actually, as they get older, they start to eat larger seeds. And once they reach adult stage, they're mainly on rice. That's you know, the most common grain in this area. But they'll eat a little bit of everything else. They'll eat minnows, they'll eat crawfish. They're from southeast Texas, they'll eat crawfish. Yes, sir.
What does a live trap look like?
A live trap, let's see, I've got one right here. Well, they make different sizes, but this one right here, I can catch a bobcat in this one. Our wildlife program has grown to involve so many species, and animals are moving in, different species that we haven't had before. This is a beaver cutting, and we have actually caught beaver in our wetlands area that were trying to dam up some culverts. It was actually our outfall canal. We had to trap the beavers and get them out. It wasn't but just a pair of them, but it wouldn't be long before you'd have a family and you'd build a dam, and then once they build in a culvert, inside a culvert is one of the hardest dams to actually take apart.
How many mottle ducks live in Texas right now?
Well, right now it's probably a little under 30,000 birds. They're really having a hard time getting a number down. They've started doing some transmitter collaring on them. What they'll do, it's like a little vest that's got a transmitter on the back. And I think Texas Parks and Wildlife put transmitters on about 120 mottle ducks to track their movement and their pattern. Whenever a mottle duck start to molt, they molt once a year, and that's when they molt, they lose their flight feathers and they can't fly. And whenever they do that, they get on deep, big water, and they gang up, and they watch these collars, and they can map them, and they see exactly where these mottle ducks are, then they can go count them.
Where can I go see mottle ducks?
Probably the best place is just in some of your roadside ditches. They're very territorial. The only time that they really gang up is whenever they do molt. Any other time they're in pairs. You can go to your local refuges like J.D. Murphy Refuge, which is a state refuge, or you can go to McFadden Refuge, and we have Anahuac Refuge. But as far as just going out and seeing one, it's more likely that you would just happen upon one than you would just go see one, because they're pretty secretive birds.
Are the birds migratory species, or do they just stay in one place, stay here?
They don't migrate. They live their whole life in about a 50-mile radius from where they were hatched. They do move around a bit, but as far as nesting, roosting, sleeping, and pairing, all at about a 50-mile radius. But as far as doing like all your other North American birds and flying to Canada or further up North America, They don't. They stay right here along the coast. And that's why they're such a bird of concern. They're kind of like the canary in the coal mine. If we watch these birds and their numbers keep dropping, that's going to tell us that there's something here that's detrimental to their lifestyle. And we need to change things to keep that bird in the area. Because we don't want to see anything go extinct. We want to make sure that we can protect all wildlife. Let's go see some ducks. That's all black-bellied whistling tree ducks, and those see the 4 and the 2 and the 2 and the 2 way back, that's all mottled ducks.
I learned more about mottled ducks.
I learned about mottled ducks and about its population.
Their population going down and up.
The population of mottled ducks is just below 30,000.
Huntsman has its own place for ducks, and they had Clemson University come here and do a study.
The mottled ducks live here and that their population has gone down.
Well, I learned more about ducks and endangered species about ducks.
Mottled ducks are unusual because they do not A. fly, B. dive, or C. migrate. The correct answer is C. migrate.
Okay guys, so welcome to today's JASON shoot. This year the JASON theme is oceans and how they affect climate. And one thing we're seeing based on the last 30 years of data is that the oceans are warming and the Earth's climate is warming. And one effect that's going to have is to melt a lot of glacial ice on our glacial ice caps. So today's theme is we're going to be looking at sea level rise because of that ice cap melting. So what we're going to have you guys do is to collect a geologic sample of what we claim is this ancient beach, and later on today we'll be at a modern Texas beach and we'll have you guys compare them and see what do you think the similarities are and what the differences are. And we have different projections of sea level rise. One thing we want to check to just see what is realistic is to look at what we know about how high sea level has been in the recent geologic past, and that's why we're at this spot today. We'll see if you will agree with the evidence, but I think we have a pretty good story that we can convince you that this was the beach about 110,000 years ago when Earth was about 2 degrees warmer and the ice caps melted enough so sea level was about 18 feet higher than it is today. So now you got your samples, but before we do the side-by-side analysis, we want you to just do a quick estimate of what kind of sediment this is. So you probably remember from your geology, there are 4 main kinds of sediment by size. Got clay, silt, sand, and gravel. Put it between your fingers and roll it around. If it's clay, you won't be able to feel it because clay is microscopic. So if you can feel it, it's bigger than clay. And if it's extremely tiny, it might be silt. But if you can feel it very well, it's either going to be sand or gravel. So can you feel any grains in there? Sand. So yeah, so this is sand, but it's pretty fine sand. So could this be a beach deposit based on being made out of sand? So wind can deposit sand, rivers can deposit it, and beach waves can deposit it. The rivers in Texas run perpendicular to the beach. Okay, so the rivers drain down to the coast and they meet the coast perpendicular. So if the coast is going east-west, the rivers are coming out of the north. Okay, so we tend to get linear deposits from rivers. We also get linear deposits from beaches, but which way do they are they oriented? Are they perpendicular to the coast or parallel to the coast? Yeah, they're parallel to the coast. Okay, so if we see evidence that they're running east-west, parallel to an east-west coast, that would be a good evidence that this is a beach deposit and not a north-south running river channel. Okay guys, so we were about 18 miles inland looking at that interglacial warm period ice age beach. We're now at the modern beach. Right behind us is High Island, which is a little town on a salt dome. So this is called High Island Beach. And you guys have now collected your own beach samples from this modern beach. What we want to do is see if there's any similarity between those and what we think was a beach from 100,000 years ago. So right now I've got some of the Ice Age beach under the binocular microscope. So take a quick look in there and remember what you saw, and then we'll talk about it.
Bunch of little granules.
It looks kind of like little ice cubes. They're pretty clear. Were they all different sizes, or were they mostly one main size?
Mostly the same size, I guess.
Yeah, so that's what we call very well sorted. It's all sorted out into just a very fine sand, and that's very typical of beach deposits. Next thing what we want to do is, who's got a sample they want to lend me for a second from the modern beach here?
Modern?
Yeah, okay. So just to make it convenient, I'm using our magnifying glass to hold our sample. And if you remember what the Ice Age sample looked like, see how this compares to that.
It's about the same.
Yeah, about the same. More nice, clear, ice cube looking grains. Those are all quartz. There are some little black ones in there. Those are called heavy minerals. And anybody see any white ones? Yeah, there's some little white things. The idea what those white things are? Yeah, pieces of shell, because we see lots of whole shells and the waves break up the whole shells. These are made out of a mineral called calcite that will dissolve in acid. And rain is acid. You know, now we have extra acidic rain from things we do, but rain's always been acid because carbon dioxide dissolves in rainwater and makes carbonic acid. And then in the soils, some more acids form from organic material being broken down. So all that acid in the soil at the Ice Age beach dissolved the fossils away, which made it harder for us to figure out it was really a beach. This is the acid that vinegar is. It's called acetic acid. And it's a weak acid, kind of like the acid rain. And if we put a seashell in it, any ideas what might happen? Let's see. Why don't you put it in there? Can you see anything happening?
You can see it like, yeah, it's like dissolving like right there.
Yeah, so
that's cool.
This is actually made out of a compound, you know, you all know about sodium chloride, which is salt, table salt. This is another salt called calcium carbonate, and the acid is making it release carbon dioxide. So those bubbles are carbon dioxide as the shell's slowly being dissolved. But we've had over 100,000 years of acid dissolving that beach sand and stripping its seashells out of it, making our work a little harder. How many of you guys are convinced that that old sand deposit was a beach, very similar to this modern beach? Yeah, I think it's a pretty convincing story, especially when we have the topographic features to go with it. Okay, I think Dr. Kruger is going to talk about another feature at this beach, and that's some interesting things about Highway 87. So we're going to switch gears and let him take over.
Okay, so the last stop you were at prior to this one was up here close to Winnie. Okay, now you saw the sands up there and you saw the sands down here. What did you conclude about the sands that were up here at Winnie? Were they beach related or not?
Beach.
So they were beach related. So that means that the beach was up here around Winnie, and the date was around 120 or so, 110,000 years ago. And then it got colder. Okay, we had our Ice Age. And so what happened is when you had the Ice Age, the ice takes up the water, doesn't allow it to go into the ocean, and so sea level starts dropping. Well, sea level dropped over a period of about 100,000 years or so, all the way down to the continental shelf here, quite a ways away from where we are now. Okay. Then what happened? It started warming again. Okay, so we got a warmer episode, and that warming episode then caused the seas to advance. They advanced quite rapidly and then stalled a little bit, slowed down, and then started rising slowly again. And the projection is, due to global warming, it will continue to increase. As we have increasing rates of sea level rise, we're going to have increasing erosion of the shoreline. I'm going to show you two maps from Google Earth. This is the most recent, 2013. This is during low tide, and you can see where the coast is. But at high tide, it comes up to where the road was. Now, Highway 87 continued on this way. It's now closed for the most part. I mean, we're able to see the remnants of it here, and we'll take a look at it, but it's pretty much closed. Now, this is actually the fourth highway they've built. They've built 3 others farther out. Let's take a look at another map, and this is from around 1970, and compare where the coast is here to where the coast was in 1970. See where the highway is? The highway was open back then. So not only do you get sea level rising, okay, but you get erosion of the coastline as well. Now, if we take a look at the map down here, what I've done is I've taken a point, looked at the difference. That difference is 107 feet. So between 1970 and today, it's at least 107 feet of erosion. This works out to about 2.4 feet per year. It's probably double that because of the tide difference. So more likely we're talking an average between this time of about 5 feet per year. Now the average along the Texas coast is about 10 feet per year. So this is a little bit less, but there's many factors. We've got to look at most of that change probably occurs during storms, major storms, hurricanes, very large storms, very erosive effects. Okay, so let's go ahead and take a walk over here and take a look at the road. Don't get your feet wet now. So, this is the road. And it's slowly eroding. You can see the, or not so slowly eroding. You can see the bits and pieces here. So, yeah, you got to keep your eyes open. What essentially you have is a situation where you've got clays, marsh clays like this underneath. And if you go out, you can walk on those clays during low tide. It's black, and you can see roots, okay? That's mostly underwater now. So that was marsh out there, okay? That was marsh. Now it's the Gulf. And soon, that's going to be the Gulf as well. Okay. One of the projects that I've been involved in is going around Southeast Texas, my students and I, looking for what's called benchmarks or survey markers. And I'm not sure if you've seen topographic maps or not, but topographic maps are essentially just like any other map, except they have these contour lines that represent lines of equal elevation. In addition to that, they have the benchmarks listed. And the benchmarks are basically located on this area, and they have a BM located next to them. The BM is essentially indicating benchmark, and then they have an X where the benchmark is. If it's an X, then it is an elevation marker. If it is a triangle, it's a position marker, okay? In order to determine the local effects, because that's what's really important to us here, we've got to find out if this ground is sinking or rising. And how do we do that? Well, we look at benchmarks that have been set in the ground many years ago. There's a benchmark in this area that was set, I believe, in 1935. Now, we can go back, and we're going to do this today, and measure the elevation we see today and see if there's any difference. We'll see if it's higher or lower or about the same. Then we could take that difference divided by the number of years, and we can determine the subsidence rate in millimeters per year, inches per year, feet per year, whatever units you want, okay? But before we can do that, we got to find the benchmark, don't we? Okay, now this is kind of like a treasure hunt. It can be lots of fun. Okay, now you did the calculations on how much difference in elevation there was. How much did it sink from when it first was set?
0.172 meters.
0.172 meters. Okay, how many years did that take? 78 years. So what is the calculation of your subsidence rate in millimeters per year?
2.
2 millimeters per year, huh?
Yes, sir.
Well, guess what? When I measured this last time, guess what I got? We're right here in High Island, and this is what's called a bubble map. And the size of the bubbles indicate how much either uplift or subsidence there's been in this area of southeast Texas. But we measured it, and I measured it before, and if you look at the color blue and the size of the dot, guess what it is? Negative 4 to minus 2, which is 2 to 4 millimeters per year. So you were spot on. We're going to be seeing a tide gauge here. And what this does is that what the tide gauge is reading is a combination of sea level rise, global sea level rise, and subsidence or uplift, in this case subsidence. So if we were trying to take the tide station readings and we get an estimate of a rise in sea level in millimeters per year, we would have to subtract the subsidence that we have in this area to get the global sea level rise. Well, we are here at Rollover Pass, a man-made cut that goes through Bolivar Peninsula. And what it does is it connects the Gulf of Mexico over there. It goes underneath here, and to the other side over here is East Bay of Galveston Bay. Now, when the tide comes in, what happens is it brings a lot of sand with it and transports a lot of sand underneath into over in East Bay. Okay, quieter water, and it deposits it. So basically, this is here, and it's creating a problem over there. It's also covering up the intercoastal waterway. And so what happens is the state of Texas wants to close this down. They want to fill it in and just make one peninsula now without this being here. Now, other entities want to keep this open because of the fishing opportunities. And so there's a legal battle going on right now. It may be here for a while longer, and it may not be, okay? But the real reason we came here was not to just discuss this, but to discuss a tide meter that's here. Not only a tide meter, but a weather station. You see that white cylinder with the antenna up there? Okay, that is a tide, it's called a tide gauge. It also operates as a weather station as well. What happens is that there's a PVC tube that goes on down, and there's a float. So as the water level rises, the float rises. As it falls, okay? That information goes into this box, and it's processed and transmitted and recorded. It tells not only when the tides go in or the tides go out, but it also tells ups and downs. As it continues to record, what happens is, as sea level rises, it'll record higher highs and higher lows. And if you track that, you could get an idea long-term what sea level rise is doing. And if sea level was falling, we could tell that sea level was falling as well. So it's these tide gauges around the world that are one of the ways that are used to determine how fast sea level is rising. Now, there's a lot of factors that influence sea level rise. Okay, they're both natural factors, but one suggestion was that around, the early 1900s, we had basically, through this period of time, the 1800s and so on, we had, the Industrial Revolution. We had quite a large number of carbon or basically greenhouse gases that were being put into the atmosphere. And so one interpretation is that these greenhouse gases that have been increasing have been causing global warming and melting of the ice of basically glaciers and causing sea level to rise. Recently, however, the suggestion is that we're going to see a lot more rapid rise as the greenhouse gases continue to build up and we continue to have more and more melting. That rate is going to increase. So we're probably going to see slopes that are going to be going up a lot steeper. So the current rate of rise is about 3 millimeters per year. Now, if we continue to pump as much or continue to pump more, then that result will get even worse. If we reduce our emissions, the projections are that we'll be able to slow it down a little bit and ultimately have less sea level rise than we are. But we've already locked in sea level rise by the carbon dioxide we have in there, the other greenhouse gases we have in there. We've already locked it in. So there's no way that we're going to escape this rapid sea level rise. It's going to happen.
Okay guys, it's been a great day. Thanks for coming. This is our last stop. And so far we've gone back to a beach more than 100,000 years old. You were just at the modern beach, and right here where the beach is going to be, we project somewhere near here in about 85 years. So in 2100, projections are sea level will rise about 3 feet. Some people have suggested even higher. Right now we're about 3 miles north of High Island, and you notice the terrain we crossed had lots of water in it. That's actually brackish water. It's intertidal, and if sea level rises 3 feet, the beach will probably be, if not at this spot, either a little farther north or a little farther south, but somewhere in this area. Based on current rates of rise, it could be even faster than that, but we can only predict based on what we've seen so far. So does anybody have any questions?
When will the beach start moving?
Yeah, you guys, you just saw Highway 87's remnants. So that was the 4th Highway 87. So 3 other ones were paved farther and farther offshore. So the beach has already started moving. Projections right now, based on the current rate of rise, would be about a 3-foot rise. And that should put the beach right here in about 85 years. So in your lifetimes, you guys are going to watch High Island become a real island and watch the beach move. Any other questions?
Is that a 3-foot rise globally?
Well, what happens when you put water into one end of your bathtub? Does just that end rise, or does the whole bathtub rise? And the ocean is a great big bathtub, and when we start adding water to it, it goes up everywhere. All the oceans rise.
We learned about the rise and fall of the oceans and how it can affect everything.
I learned that there are markers put in the ground so you can tell how high or low that the elevation is.
Fossils are not present in surface sands from hundreds of thousands of years ago.
The reason there aren't any fossils in like prehistoric beaches is because the acid has eroded them away.
2 different sands from 100 years ago and modern sand, they're both the same still. Just because of the glaciers melting, it doesn't mean just one part of the ocean rises, it's all rises the same equal amount.
A sea level rise of 3 to 5 feet in southeast Texas will cause our beaches to move inland several A, feet, B, miles, or C, meters. The correct answer is B, miles.
Thanks for coming to this year's JASON program.
And be sure to come back for next year's JASON event.
If you would like to be a National Argo, visit www.jason.org for details.
Remember, JASON needs Argos like you for national JASON missions.